So, in the last few classes, we have talked about the neural networks and the application of neural networks for pattern recognition. Particularly, we have talked about two types of neural network. One was the Hopfield neural network, where we have said that the Hopfield neural networks are basically meant for binary feature vectors. So, if I have a number of binary feature vectors, the Hopfield neural network basically learns or remembers those feature vectors by updation of weights. So, learning process is basically updation of weights. And in case of backpropagation neural network, the learning is also by means of updation of weights, but for backpropagation or feed forward neural network, the neural network is not confined to the binary feature vectors only. It considers the feature vectors which contains real components also. Now, when we talked about the feed forward neural network or backpropagation neural network, we have said that it is a multi-layer neural network, which has got one layer which is input layer, and it is just a buffer layer whose responsibility is to just pass the information to the layers above it. And in the simplest case of backpropagation neural network, we had single layer perceptron, which consists of only one output layer in addition to the input layer. So, the neurons in the output layer, so if I just draw it in case of a single layer perceptron, the network architecture of single layer perceptron was something like this. We had an input layer and we had an output layer. So, the number of nodes in the input layer is same as the dimensionality of the feature vector, or if the feature vector is of dimension d, then the number of nodes in the input layer is d plus 1. So, one node is to take care of the bias term, and the number of nodes in the output layer is same as the number of classes. So, the network architecture was something like this. From each input layer node, we had a connection to every output layer node. So, it was something like this and so on. So, the feature vector is fed to the input layer nodes. And one of the node was kept at a constant value which is equal to 1, that is meant for feeding the bias term. And outputs of these different nodes in the output layer, they indicated the corresponding class, say C I. Every node in the input layer is connected to every other node in the output layer through a connection weight, say W I j. So, ith node in the input layer is connected to the jth node in the output layer through a connection weight W I j. So, during training, what we had done is we had fed the feature vectors for which the classes are known, and if the class of a feature vector is known, that means I know that what should be the output corresponding to that particular feature vector. So, that output is an output vector, say t, and when the network is not properly learned, in that case for an input vector I get an output which may not be equal to t. So, I get an output which is say O, whereas t is the target output. So, I have an error E which is equal to square of this, right. So, during training of this backpropagation neural network, what we had done is we tried to minimize this error E by means of updating these connection weights. So, this was expressed as a function of a set of connection weights w I j, and then through gradient descent procedure we have reduced the error by updation of the connection weights w I j. In case of multi-layer perceptron, we had the same input layer is always possible. We also had the number of nodes in the output layer, which is same as the number of classes. In addition, we had one or more hidden layers. Okay. However, the connection pattern remains the same. Every node in the input layer is connected to every other node in the layer above it. So, it continued this way. And so on, and finally, we get the output. However, the training for this backpropagation neural network was same as a single layer perceptron. That is, we for a known feature vector which is input to this neural network, we know what is the output or we know what is the target output. And when the neural network is not properly learned, we get an output for the same input feature vector, which is not same as the target output. So, there again we get an error, and this error when I express in the form of a function of the weight matrix or the connection weights, then we try to reduce that error by optimizing or by adapting the weights. And when we modify the weights, when we adapt the weights, the error information for reduction of the error that propagates from output layer to input layer. So, it propagates in the reverse direction. So, it is like this: the error information or the weight updation information that propagates from the output layer to the input layer. Okay. So, that is why it is called back propagation learning. But during the classification, the information moves from the input layer to the output layer. So, the information is fed from input to output. So, that is why it is feed forward network, whereas the learning algorithm is called a back propagation learning algorithm. Now, when we discussed about this feed forward network or back propagation network, we have said that if the patterns or if the classes are linearly separable, then a single layer perceptron is sufficient. But if the classes are not linearly separable, then single layer perceptron is not sufficient. We have to have one or more hidden layers. Okay. And what these hidden layers do is, it represents a non-linear boundary by a set of piecewise linear boundaries. And to explain this, we have taken few examples. We have taken an AND function. So, in case of AND function, if I represent the AND function as a two-dimensional binary vector, so I have the input components 0 0 0 1, 1 0 and 1 1. So, if the function is an AND function, only when the input is 1 1, the output is 1. In all other cases 1 0 0 0 or 0 1, the output is 0. Now, if this AND function we consider to be a classification problem, then you find that it is quite obvious. I can draw a straight line separating the set of zeros and the set of ones. So, that means the input vector 1 1, that is put in one class, and all other combinations of the input components, that is 0 0 0 1 or 1 0, that is those are put in another class, and I can separate these two classes by a straight line. So, that means that this particular function AND function is a linearly separable function. Similarly, if I take an OR function, here again I put it as x 1, x 2, somewhere here let us put 0, 1, 0, 1. So, only in case of 0, 0, both x 1 and x 2 components, when they are 0, the output is 0. In all other cases, the output is 1. So, I have this type of situation. And again here you find that I can separate the 1s and the 0 by a state line. So, which clearly indicates that this is also a linearly separable problem. But we have faced difficulty in case of XOR function. So, in case of XOR function, if I put it in the same fashion, I have x 1, x 2, 0, 1, 0, 1. So, when the input is 0, 0, the output is 0. When the input is 1, 1, output is also 0. When the input is 0, 1 or the input is 1, 0, the output is 1. Now, given this type of situation, you find that I can no longer separate the outputs zeros and 1s by single state line. Rather, I need to have two different state lines over here to separate the zeros and 1s. So, this clearly says that the XOR function is not linearly separable. And when we discussed about this backpropagation neural network, we have said, we have shown the AND function and OR function, they can be represented, they can be implemented using single layer perceptrons, but when you go for XOR function, the XOR function cannot be implemented by single layer perceptron. Rather, we need at least one hidden layer for implementation of XOR function by a feed forward neural network, because it is not linearly separable. Okay. So, now today we will discuss about another kind of network, which is called radial basis function network. So, what radial basis function network does is, it performs a nonlinear transformation over the input vectors before the input vectors are fed for classification. So, by using such nonlinear transformation, it is possible to convert a linearly non-separable problem to a linearly separable problem. It is also possible, what this RBF network or radial basis function network does is, it increases the dimensionality of the feature vectors. Okay. So, I will come to that later. First, let us see that how this introduction of nonlinear function to the input feature vectors before we go for classification can make a linearly non-separable problem, can convert a linearly non-separable problem to a linearly separable problem. So, let us just take a situation something like this. Say I have a set of feature vectors which are of this form. Okay. So, here you find that if I say that all these green crosses represent feature vectors belonging to one class and all the red crosses represent feature vectors belonging to one class, another class. So, clearly you find that these two feature vectors cannot be separated by a state line. Rather, what I need to have is, I have to have a curve, a quadratic curve at least, to separate these two classes. Now, if I impose a nonlinear transformation something like this, that a transformation which will expand the feature vectors in this direction and contract the feature vectors in this direction. So, if I do this, these feature vectors will be converted, will be clustered into a cluster something like this, and these feature vectors, it is possible they will be clustered into a cluster like this. And because of this nonlinear transformation, now it may be possible that I will be able to find out a straight line which separates these feature vectors from these feature vectors. Okay. So, that is why I say that if I use a nonlinear transformation, if I impose a nonlinear transformation to the feature vectors, before I put them, go for classification purpose, then it may be possible that a nonlinearly separable problem can be converted to a linearly separable problem. The other one, as I said, that the RBF network, the radial basis function network, also increases the dimensionality of the feature vector, because it has been found that if we increase the dimensionality of the feature vectors, then a classification problem which is linearly non-separable in a lower dimensional space, it may be possible that they will be linearly separable in a higher dimensional space. And more you increase the dimension, the linear separability, the possibility of linear separability increases. So, it is simply like this. If I put it in this form, so the tips of my finger, they represent different feature vectors, and the tips of the fingers of the left hand, they represent feature vectors belonging to one class, and the tips of the fingers of the right hand, they represent feature vectors of another class. And these feature vectors, they are coplanar. So, all of them are lying in the same plane. So, if the situation is like this, obviously, this set of feature vectors are not linearly separable. However, if I introduce a third dimension, something like this, I push one on the forward and the other one backward. And in this third dimension, now we find that they are linearly separable. So, this is just a simple logic that if I increase the dimensionality, then it is possible to increase the possibility of linear separability among the classes which are linearly non-separable in lower dimensional space. So, the RBF network actually imposes both. It imposes a nonlinear function, a nonlinear transformation to the feature vectors, and it also increases the dimensionality of the feature vectors. So, if I have a set of feature vectors whose original dimension is a dimension p, I increase the dimension of the feature vectors to dimension m. Okay. So, how it is to be done? A given feature vector x is subjected to a function phi. So, phi of x, where this phi of x is of the form phi 1 x, phi 2 x, phi 3 x up to phi m x. Okay. So, if the original feature vector x is of dimension p, for each such feature vector x, I impose this set of phi functions, m number of phi functions, and each of these phi functions produce a real value. So, as I have m number of phi functions, so by application of this phi function onto this feature vector x, I create m number of real valued components. So, what I get is an m dimensional feature vector, and if m is greater than p, then obviously I am increasing the dimensionality of the feature vector from P to M. And in case of radial basis function, each of these phi function, whether it is phi 1, phi 2, phi 3 up to phi m, each of these phi functions are radial basis functions. Then what is a radial basis function? So, let us try to see what is a radial basis function. Every radial basis function has a receptor. So, the radial basis function has a receptor, say t, and as I move radially away from this receptor, the value of the function goes on increasing or goes on decreasing. And the value at a point depends upon the radial distance of the point from the receptor t. Value of the function is either maximum or minimum at location t. So, if I put concentric circles around this receptor t, the value of the function phi on these each of these concentric circles are constant. So, there are different choices of radial basis functions. I can put those radial basis functions as one of them is called multi-quadrics. Let me put which is given by phi of r is equal to r square plus c square to the power half for c greater than 0. Then I can have inverse multi-quadrics, where the function phi r is given as just inverse of quadrics, that is r square plus c square to the power half for c greater than 0. I can also have use Gaussian functions. Where phi of r is given as exponential minus r square upon 2 sigma square for sigma greater than 0. And this r is a measure of the distance of the point from what I said as the receptor of the radial basis function. So, this r, if I want to compute this radial basis function at a point say x, say coming over here, if I want to compute the radial basis function at a point x, where t is the receptor of this radial basis function, then r is nothing but t minus x or x minus t, which is nothing but the distance between x and t. So, you find that in all these different cases, if I use this multi-quadrics, then at r equal to 0, the value of the radial basis function is equal to c, which is the minimum. And as r goes on increasing, the value of the radial basis function goes on increasing. So, the nature of the radial basis function for multi-quadrics will be like this. When you go for the inverse multi-quadrics, at r equal to 0, That means, when the point x and the point t they coincide, that is at the receptor point, the value of the inverse multiquadrics is minimum, which is nothing but 1 upon c. Sorry, this is the maximum, which is nothing but 1 upon c. And as r goes on increasing, the value of the radial basis function goes on decreasing. So, the nature of the function with inverse multiquadrics will be like this, just inverse of multiquadrics. In case of Gaussian function, you all know that this has a very common form. The Gaussian function will be something like this. So, at the receptor location t, the value of the function phi will be maximum, and as you move away from the receptor point, the value of the function phi r that goes on reducing following this pattern. And it is this Gaussian function which is most commonly used in case of radial basis function. Now, let us see that how, by using this radial basis function neural network, we can convert a linearly non-separable problem to a linearly separable problem, even keeping the dimensionality of the feature vector same. So, for doing that, I will use the same XOR problem. So, I have this x 1, x 2, here I have 0, here I have 1, again 0, here it is 1, I have 0 over here. Okay. So, these are the outputs of an XOR function. What I will do is, I will use a radial basis function to nonlinearly transform these feature vectors into another space, and the radial basis function that I will use is a Gaussian basis function. So, the form of the radial basis function will be phi x, which will be given by e to the power minus x minus t square. Okay. And this t is the receptor, and as I said that I will not increase the dimensionality. So, I will use two of the receptors. One of the receptor I consider is this point at location 0 1, and other receptor I consider this point at location 0 2. So, by using this, if I compute the nonlinear transformation, then the values that I will have will be something like this. I use this nonlinear transformation. So, I will put these inputs, my inputs are 0 0, 0 1, 1 0 and 1 1, and I will have the output functions. One is phi 1 and the other one is phi 2. So, if I say that this is my T 1, the receptor T 1, and this is my receptor T 2. So, phi 1 x will be simply e to the power minus x minus T 1 square, and phi 2 x will be e to the power minus x minus T 2 square. So, here you find that I assume that 2 sigma square that is equal to 1. Okay. However, that does not matter for this nonlinear transformation. So, you find that when it is 0 0, okay, then what will be my phi 1 of 0 0? Phi 1 of 0 0 will be simply equal to sorry, let me use the receptors as this. Let this be T 1 and let this be T 2. Okay. So, phi 1 of 0 0 will be equal to 1, and if you compute this term, phi 2 of 0 0 will be 0.1. Phi 1 of 0 1 will be equal to 0.4, and phi 2 of 0 1 will also be equal to 0.4. Phi 1 of 1 0 will be 0.4, this will also be 0.4, and for 1 1, phi 1 will be 0.1 and phi 2 will be equal to 1. So, this is the kind of situation that I will have. So, what I have used is this 0 0 has been used as one of the receptors of the radial basis function, and 1 1 has been used as another receptor of the second radial basis function. So, obviously, 0 0 as it coincides with my receptor T 1. So, I have the situation that x minus T 1 square, that will be equal to 0. So, this is e to the power 0, which is equal to 1. So, phi 1 of this x, which is 0 0 which is equal to 1. Similarly, if I compute phi 2 of x, that will be equal to 0.1. For 0 1, phi 1 of x will be 0.4, phi 2 of x will also be 0.4. For 1 0, which is this point, phi 1 of x will be equal to 0.4, phi 2 of x will also be equal to 0.4 because of these exponential functions. For 1 1, if x is equal to 1 1, this coincides with T 2. So, phi 2 of x, this distance being equal to 0 now, phi 2 of x will be equal to 1, and phi 1 of x, where this is the receptor, the phi 1 of x will be equal to 0.1. So, you find that 0 0 has been mapped to 1 0.1, 0 1 have been mapped to 0.4 0.4, 1 0 has been mapped to 0.4 0.4, 1 1 has been mapped to 0.1 1. So, if I plot this, the kind of plot that I have is zero 0 is now mapped to 1.1, which will be somewhere over here. This is my x 1, this was my x 2. Now, this will be phi 1, instead of x 1, it will be phi 1, and this will be phi 2. So, this is phi 1 of x, this is phi 2 of x. So, 0 0 has been mapped to 1.1, 0 1 has been mapped to 0.4, which will be somewhere over here, 1 0 that is also mapped to 0.4, it is the same point. So, both the points have to be now has been mapped to the same point in phi 1 phi 2 domain, and that has happened because of the nonlinear transformation, whereas 1 1 has been mapped to 0.1 somewhere over here. So, this is 1. This being the situation, now we find that I can draw a straight line separating these points. So, a problem which was not linearly separable in original space, it has now been linearly separable in phi space, simply by using a nonlinear transformation. And the possibility of the linear separability between the classes increases as we go on increasing the dimension of the feature vectors by using this phi functions. So, by using this, now the architecture of the network will be of this form. We have the input layer as before, it always has to be present because this is the layer which accepts the input vectors and feeds to the next higher layers. We will have only one hidden layer, and the number of nodes in the hidden layer will be equal to m, where m is the dimension to which we want to increase the dimensionality of the feature vectors. So, if I have p is the dimension of the input feature vectors, we have p number of nodes at the input layer, and if m is the increased dimensionality, then m is the number of nodes in the hidden layer. Each node in the hidden layer actually performs a radial basis function, and as we said, so it is something like this. Each node represents or computes a radial basis function, and in the output layer we will have number of nodes which is same as the number of classes, say C. Now, from each node in the input layer, I have a connection to each node in the hidden layer, and from each node in the hidden layer, I have a connection to each node in the output layer. Finally, I have outputs from the classifying neurons, and here I feed the input feature vectors. So, this is what is the architecture. So, the nodes in the hidden layer, they actually perform the radial basis function, and nodes in the output layer, they perform linear combination of the outputs of the hidden layer nodes. So, here I will have a linear classifier. So, actually classification is done only at the output layer, whereas at the hidden layer only we perform the radial basis function. So, that is a transformation of the input feature vector to a hidden space, because this is in the hidden layer. So, you can say that it is a transformation to a hidden space. So, when I have a number of nodes in the hidden layer which performs radial basis function, okay. So, I have two levels of training. The first level of training is training of the hidden layer nodes. So, what does this training mean? As every node in the hidden layer is a radial basis function. So, for each of the radial basis function, I have to have a receptor T. So, one of the purpose of training of the hidden layer nodes is to find out that what should be this receptor T. And then if I use the Gaussian function, then we have said that the radial basis function is of the form e to the power minus r square upon 2 sigma square. So, that is what is my phi of x, where this r is nothing but the distance between x and t. So, this sigma actually indicates that what is the spread of this radial basis function. So, that is also what is to be trained. So, by saying that I want to train the hidden layer nodes. For each of the nodes, I have to find out what is t, and for each of the nodes, I have to find out what is the sigma. So, that is what is meant by training of the hidden layer nodes. And at the second level, I have another training operation by which I have to train these weight vectors, which connects the outputs of the hidden layer nodes to the output layer nodes, because it is the linear combination of the outputs of the hidden layer nodes which decides that to which class a sample will belong, and that will be outputted, that will be available at the output of the output layer nodes. So, let us see that how we can train node in the hidden layer. Okay. So, by saying that the hidden layer nodes are to be trained, let us see the situation that we have. If I go for supervised classification or supervised learning, what I have is I have a set of feature vectors or which are labeled with its class belongingness, which are to be used for training the neural network. In case of multi-layer perceptron or in case of single layer perceptron, we did not have any nonlinear transformation. So, from the level of the input feature vector and actual level that you got at the output of the output layer nodes, we have defined an error function, and our aim was that by updation of the connection weights, we have to reduce that error function or we have to minimize that error function. So, the algorithm was that in order to minimize the error function, how the connection weights are to be modified, and that modification of the connection weights was carried out from the output layer to the input layer in the backward ways. Whereas, in case of RBF network, the training consists of two parts. The first one is training of the hidden layer nodes, and when I say it is the training of the hidden layer nodes, that means for every hidden layer which represents a radial basis function, I have to find out that what should be the receptor, and also I have to find out what is the spread of the radial function of the radial basis function, which is sigma. So, if we are given a number of training vectors, so we are given n number of training vectors, okay, varying from say x 1, x 2 up to say x n, we have n number of training vectors, where each of these vector is of dimension p, and I want to transform these vectors to a vector of dimension capital M. Okay. So, naturally, at the hidden layer node, at the hidden layer I have to have capital M number of nodes, and when I have this capital M number of nodes, so for each of the nodes I have to have a receptor. That means, for the ith node I have to have receptor T I. So, I varies from 1 to up to M, and the ith hidden layer node I have to have sigma I, again I varying from 1 to up to capital M. So, I have to have T number of M number of receptors, I have to have M number of variances or standard deviations. So, this can be done in various ways. The simplest way is at random from the training samples, you pick up m number of samples which are to be used as deceptors, which is not very logical. Rather, what appears to be more logical is you go for clustering of this capital N number of training samples into m number of clusters. So, when I go for clustering, I basically get a space where it is more likely to have a feature vector. Clustering we have not discussed yet, but I will just for the purpose of completion of this lecture, I will simply indicate what does this clustering mean. So, I have capital N number of samples, from that I have to form capital M number of clusters. So, it is understood over here that this N has to be greater than capital M. If N is less than M, that is number of samples, training samples is less than the number of clusters that are to be formed, it is not possible. Because even if in a single cluster, I assume that there has to be only one feature vector, at the most I can have n number of feature vectors, or at the most I can have n number of clusters. Okay. So, I cannot form number of clusters which is more than the number of feature vectors which is provided. So, obviously, our assumption is that the number of feature vectors n is greater than the number of clusters that one has to form, that is m. Now, there are various clustering algorithms. One of the clustering algorithm is, say initially I partition this n number of samples into capital M number of clusters. Okay. So, every cluster will have a number of samples. For each of the created clusters, say suppose I have got a number of feature vectors which are given like this. So, these are the set of feature vectors. Now, suppose I want to form 3 clusters. So, initially what I do is at random arbitrarily you divide this set of samples, you partition this set of samples into 3 different clusters. So, this cluster contains these samples, this cluster contains these samples, this cluster contains these samples, and so on. Now, once I have these initial clusters, then what I can do is for each of the cluster so formed, I compute the cluster center. So, which will be the representative of that cluster, of the samples belonging to that cluster. So, if over here suppose the center of this cluster comes out to be somewhere over here, the center of this cluster comes out to be somewhere over here, and the center of this cluster comes out to be somewhere over here. So, this will be the center cluster center mu 1, this will be the cluster center mu 2, this will be the cluster center mu 3, and so on. Now, once I form these cluster centers, in the next iteration, what I do is for each of the samples, I find out which cluster is nearest to that particular sample. So, here you find that it may be possible that this particular sample, say this particular sample, its distance from mu 3 is less than its distance from mu 2. So, initially though this sample was put in cluster 2, in the second iteration, because its distance from the cluster center 3 is found to be less than its distance from the cluster center 2, this sample will be moved from cluster 2 to cluster 3. And this operation you perform for every sample. So, for each such sample, you find out that what is its nearest cluster center, and you move this sample to the cluster whose center is nearest to it. And you perform this for each of the samples. So, at the end of second iteration, you will find that initial clusters that we had formed, the samples in the initial cluster have changed. I still have 3 number of clusters, but the sample values have changed. So, in the second iteration, at the end of second iteration, again I compute that with this new set of samples, what is its cluster center. After computing recomputation of these cluster centers, again I go for reassignment of the feature vectors based on its distance from these new cluster centers. And this operation you perform in a number of iterations, and finally, when it stabilizes, then we say that the clustering is complete, and at that point whatever cluster centers I have, those cluster centers are my receptors. So, by this what I have done is, for each of the radial basis functions or each of the nodes in the hidden layer, I have computed the receptors. These receptors are nothing but the cluster centers. Once I do that, next what I have to do is, I have to, so for every ith node I have to compute a Ti. I have found out what is Ti. Next I have to find out what is sigma I. So, then what I can do is, I can go for a nearest neighbor rule. From every Ti, I find out say p number of nearest receptors, and the distance of those p number of nearest receptors. So, I get p number of distances, and root mean square of all these distances, I can take that as the variance or the standard deviation sigma I. Okay. So, if I am interested to find out what is sigma j, what I will do is, I will take T j minus T I, take the square of this, sum of this for I is equal to 1 to p, as I have p number of nearest T i's, 1 upon p of this and square root of this. This is one of the way in which I can compute sigma I. So, I have the receptor T I and I have sigma I. So, once I have this T I and sigma I, then you find that in the middle layer, every hidden layer node is defined. For every node I have T I, for every node I also have sigma I. So, here also I have T I, I have say T j, here also I have sigma j. So, this is defined for every node. So, now if I feed any feature vector x to this, I have the corresponding phi 1 of x, I have the corresponding phi 2 of x, I have the corresponding phi m of x. So, the original feature vector x is now converted to an m dimensional feature vectors. Now, using these feature vectors, I have to go for classification. Okay. So, for that I have to train the output layer of this radial basis function neural network, because as you see, if you remember the architecture of the radial basis function neural network, over here I had a set of weights w. So, I have to compute these w's for classification purpose. Now, here as we said that as I increase the dimensionality and as I impose the nonlinear transformation and increase of dimensionality taken together, that increases the possibility that the classes will be linearly separable in the higher dimensional space. And as I increase the dimension, as I increase the value of m, the possibility of linear separability goes on increasing, but I do not know that how many such radial basis functions I have to use, so that my original problem becomes linearly separable. So, though I have increased the possibility of linear separability, I have not been able to guarantee that they are linearly separable. So, the best way to find out these connection weights at the output layer is by means of least mean square error technique. So, what we have is, we have already discussed about the LMS technique, and there we have seen that if y is a set of feature vectors and if I have a set of feature n number of feature vectors y, then using this y I can form a matrix. Okay. So, let me say this feature vector is x. Okay. So, if I have n number of feature vectors, every feature vector when I put in the form of a row, I have a matrix of say n by d, if d is the dimensionality of the feature vectors, and we call this matrix as y. And the logic that I put is, when I want to train say first output node of my classifier, only the samples, if I feed a sample which belongs to class 1, only that output should be 1, the rest of outputs will be 0. So, for every input feature vector, I can define an output vector. Okay. So, using each of these outputs, I can define what in case of this LMS algorithm we have said as a bias vector, and then by using the pseudo inverse technique, I can find out what is the output weight. So, this discussion I will stop here today. I will continue with this discussion in our next class. Thank you.